is Drew Desker. I'm the director here. It's great to have you up here on a, well, relatively cloudy night, but I think some of you actually got a chance to see Saturn. Yes? All right, excellent, excellent. We are, believe it or not, approaching our 50th anniversary as an organization. 50 years ago, over 50 years ago, there's a group of Polish immigrants, people of Polish heritage, wanted to commemorate Kopernik's 500th birthday. Now, we know Kopernik's name as Nicholas Copernicus. That was actually his academic name. And actually, that brick wall you see over here is actually part of the original building. But anyway, we are approaching our 50th anniversary, and we have a lot of good things coming up. But just a little background about Kopernik. Well, let me see here, actually. Who's here for the first time? All right, good number of people. Okay, who here are members? Almost the rest of you, okay. Very good. Well, anyway, the people who raised their hands second actually have a piece of valuable information about how valuable Kopernik membership is. We belong to what's called the Association of Science and Technology Centers. It's a consortium of 350 other science centers throughout the country, and actually even spread out throughout the world, that will honor a Kopernik membership. So if you like this kind of place, getting a Kopernik membership is actually very cost effective. In fact, my daughter and I went down to the Franklin Institute down in Philly a few years ago. Had we paid the street price for just an adult and a student, it would actually cost me more than our family membership would have cost for that one day. And but you could go to the Robeson Museum and Science Center. You could go to the Corning Museum of Glass. You could go to the Intrepid down in New York City. So if you like this kind of place, you might want to consider getting a Kopernik membership. Kopernik is really all about sort of lifelong learning. We offer programs for kids as young as 3 years old through adults, you know, that really want to pursue lifelong learning. It's and these Friday night programs are really what that's all about. It's not always about astronomy, although tonight the program happens to be about astronomy. In a couple of weeks, we actually will have a local physician talk about concussive brain injury. The week before that, we'll actually have somebody doing a TikTok, as in T-I-C-K, T-A-L-K, and actually talking about Lyme disease. And as I said, it's not always about astronomy, and it's an opportunity to learn something perhaps that you've might not know about or might want to learn more about. So we welcome you to come back on a Friday night. Again, always at the end of our programs, if it's clear, or even partially clear, we'll open up our scopes and see what's out in the sky to see. One of the other things we do is, and this sort of really started, actually COVID sort of forced our hand on this. Back in 2020, we had a whole bunch of speakers lined up for Friday nights, and then COVID shut us down. So we figured, well, we'll just wait a couple of weeks, wait this thing blow over, and well, that didn't quite work out that way for us. So he said, look, we still want to continue our outreach, so we actually started having the people that were presenting Zoom into us here, that we would then turn it back around, put it out on our YouTube channel. Now we have over 13,000 subscribers. And so not only do we do things like our Friday night programs, but we also will do special events. So in fact, tomorrow we will be live streaming for the partial eclipse. Now, if the clouds miraculously separate, we will actually have a camera on one of our scopes, and we'll be putting that out on the live stream. But we'll also have the capability of bringing in like NASA live streams or other sites live streams. Actually, one of our educators is actually down in Texas right now. In fact, we just tested with her earlier this evening. So we will actually we'll be able to see her live stream camera, and we will be putting that out on our YouTube channel. So we invite you to come back tomorrow. Tomorrow is when we can, if you come back tomorrow, you can get your Eclipse glasses. And it's part of the admission. We don't sell them, they're part of the admission. Anyway, Friday nights is really an opportunity again to learn get deeper into a particular topic that we're happen to be exploring that evening. We're very fortunate to have Dr. Susan Higley, who is our Director of Education, and also is a NASA partner Eclipse ambassador. And I'm going to just pass it right over to Dr. Higley, and also will be joining us will be Dr. Martha Saladino, and she's up on Zoom, and there we go. Hello, Martha. Actually, everybody wave to Martha so that she can. Okay, there you go.
Hello, how are you doing today?
All right, so Dr. Higley, the podium is yours.
Dr. Martha Irene Saladino is an education and outreach scientist at the Space Telescope Science Institute, where she supports the outreach efforts of different NASA missions and projects, mainly the upcoming Nancy Grace Roman Space Telescope and Girls Steam Ahead with NASA. Martha Irene obtained her PhD in astrophysics at Radboud University in the Netherlands, where she developed cool numerical simulations of evolved sun-like double stars. Her passions are to make scientific content accessible for non-English speaking audiences, engage underrepresented groups in science, make visible the work of underrepresented groups in science, and show the diversity of people in astronomy as a means to create role models. Martha Irene will be telling us why eclipses are important for science. Dr. Saladino, the stage is yours.
Thank you very much. I'm going to start sharing my screen. Hopefully you will see what I want you to see. There we go. Can you see everything just fine? I'll take it to see yes. So hello everybody, my name is Martha, and I was already introduced. I'm not going to reintroduce myself. I'm just going to be talking today about eclipses in science. So probably all of you are pretty excited about the eclipse that is going to be visible tomorrow in many states in the US. So hopefully I can give you a small introduction to eclipses in our solar system and in general. So let's start with eclipses in our solar system. So first of all, what is an eclipse? So the word eclipse comes from the Greek word eclipses. I hope I'm pronouncing this correctly, which means to leave out or to abandon. In this case, we're not really abandoning anything, but we're leaving out certain thing, an object in the sky. So basically, an eclipse occurs when a body in the sky, such as the moon or a planet, move into the shadow of another another body in the sky. So here we have, for example, the moon is eclipsing Earth, the sun from Earth in this small video. Now, there are different types. Can you hear me just fine? Okay, perfect. Okay, there are different types of eclipses on Earth, and they occur when the sun, Earth, and the moon align on a straight or almost straight configuration. So the order they are in determines the type of eclipse we have. For example, we can have a lunar eclipse, and that happens when the moon is behind Earth, and then Earth is blocking the light of the sun to reach the moon. Or we can have a solar eclipse, and that happens when the moon is in front or in between the sun and Earth. So here I'm going to be focusing now on solar eclipses, because we have three different types of solar eclipses. One of them is called solar, like the total eclipse. The other one is an annular eclipse, and the final one is a partial eclipse. So during the total solar eclipse, the sun, the moon, and Earth are perfectly aligned. And then the moon covers the entire disk of the sun. So everything that is visible in this case is just what we call the solar corona. This is like the atmosphere of the sun. So this will create a small circular shadow on a small part on Earth, and people who are there in that shadow, they are going to witness the total eclipse. And everything will be darkening at this point, and all they will see is going to be the corona. Now, remember that Earth and Moon are moving, so the shadow will also move, and it will create something that is called the path of totality. So everybody on Earth who is in this path of totality are going to experience a total solar eclipse. During an annular eclipse, what happens is that the Moon passes in front of the Sun, but the Moon is slightly further away. And because it's slightly further away, it cannot cover the full area of the Sun. So we just perceive it as the Moon blocking the Sun, but there's a small disk around it, and that's what we call the ring of fire. This is the type of eclipse that we will have tomorrow, and that will be visible in many parts in North America and South America. And finally, during a partial solar eclipse, the three objects, Moon, Sun, and Earth, are not perfectly aligned. So only part of the Sun is covered by the Moon, and it looks as if the Moon is taking a little bite of the Sun. So these are the types of solar eclipse that we can witness from Earth. But there are other types of eclipses in the solar system. So Earth is the only rocky planet where we can witness a total solar eclipse. Venus and Mercury are also rocky planets, but they don't have moons. And because they don't have moons, we wouldn't be able to see any eclipses from them. However, Mars has two moons, but they are too small, and they are not at the right distance to completely block out the disk of the Sun. Because of this, and in the video that you are seeing here, the type of eclipse that you would be able to witness from Mars would be an annular eclipse. So this video that you saw here was captured by the Perseverance rover in Mars in 2022, casting a shadow on Jupiter's surface. So if we were there, we would be able to see it. If we were under the shadows, we would be able to see some solar eclipses. Now, there are other types of eclipses in the solar system, but they are not the way we think about them. So these are called transits. So a transit occurs when a planet is passing between a star and the observer. From Earth, a transit can be observed when Mercury or Venus pass in front of the Sun, and they will obscure a small portion of the solar disk. Now, bear in mind that, for example, when Venus transits in front of the Sun, it really just covers a small portion, as you can see in this picture. But in reality, Venus is, for example, way bigger than the Moon. The only reason why we see it so small is because it's very far away, so we perceive it just very small. The last transit that happened of Venus was in 2012, and the event lasted about 6 hours. So it was the time it took Venus to cross in front of the Sun, from our perspective. The next transit that will occur, the next transit from Venus is going to take place in 2117, so many years from now. Now, what can scientists learn from solar eclipses? Well, we can learn lots of things. And I'm not an expert, but I'm just going to give you an overview of the things we can learn. So one of the things we can learn is more about the solar structure. So we can decipher the sun's structure and all the explosive events that occur in the sun. Our sun is a very dynamic star, so it's not still. It's moving like I'm moving my arms super constantly. Our sun is also, it's not quiet. So it goes through something that we call the solar cycle, and it lasts approximately 11 years. So what is the solar cycle? So during this cycle, basically, there are some levels of solar radiation and ejection of solar material are changing constantly, and they reach a maximum and then they reach a minimum. So it's basically out like the activity that the sun is experiencing, and it lasts 11 years when they have a maximum and they have a minimum. Now, during this time, the sun is ejecting material, and we call this material that the sun is ejecting a solar wind. So the solar wind can affect something that we call space weather. So yeah, there's also water in space, and the sun, like these eruptions the sun is having, can affect the space weather. We can see this solar wind that the sun is ejecting on Earth in the form of aurora borealis, or the northern lights. They also occur in the south of the planet, They are southern lights. That's why I'm calling them the aurora. So if we understand like how the sun behaves, we can also understand the effects that it has on the solar system, on our own atmosphere, and we can also help the studies of other stars in the universe. Now, another cool thing that has happened thanks to an eclipse, or that we have learned thanks to an eclipse, was the discovery of helium. Helium was discovered in 1868 by a French astronomer whose name was Pierre Janssen. So during an eclipse that he observed from India, he was studying the spectrum of the sun. The spectrum is basically something that astronomers use a lot to learn more about the elements that make up a star or a planet. And how do we create this spectrum? Well, it's as if you were pointing a prism to some light, and then when the light passes through the prism, it's split, and it's split in all its components. So it creates a rainbow. So while this astronomer, Pierre Janssen, was studying the corona, the light coming from the corona of the sun during this eclipse in 1868, he noticed a new line in the spectrum that nobody had seen before. At that point, helium had not been discovered on Earth. Even though helium is a very abundant element in the universe, on Earth, it was not known. So this is the reason why helium has this name. The name is derived from the Greek helios, that means sun, because it was in the sun corona that helium was first detected. Now, another cool thing that we can learn from eclipses is how our atmosphere works. So our atmosphere is made of different layers, and one of them is called the ionosphere. This is a layer of the Earth's atmosphere that contains a very high number of ions and free electrons, and these are able to reflect radio waves. As you can see here, for example, from one tower to the other, the radio waves are reflected. But when a solar eclipse occurs, the ionosphere cools down. And then this causes all the gases that are over there to recombine, and they become less conductive. And then the radio waves that are passing or are being reflected through the ionosphere change. And this affects the way that signals are propagating between space and the ground. So this can cause disruptions in our communications. So from these eclipses, we can also learn how we can improve our communications, or what to do when a solar eclipse occurs to prevent this, that our communications get affected. Now, another cool thing that astronomers learned from an eclipse is that Einstein's theory of relativity was correct. So Einstein's theory of relativity proposed that gravity is not a force, but is a geometric distortion in space-time. So think of space-time as a sheet, a blank, or a blanket. Now, if you have a very heavy object in your blanket, for example, let's assume that we have a bowling ball, and it's very heavy, so it will curve the blanket in which you are putting it, right? And then if we put another object, a less massive object, in this blanket, because there is a very heavy object that is curving the blanket, the trajectory of this other object, the other object is going to move, and it's not going to be still, right? It's going to be deflected. So the more mass we have to produce the gravity in a body, the more distortion we get, and that happens in space-time. So the distortion basically changes the trajectory of objects, and that also includes the trajectory of light. So general relativity predicts how much light should bend when it passes near a very massive object. But how could they prove that Einstein's theory was correct? Well, he said how much this bending in light should be, but how could we be sure of that? Well, the most massive object that we have nearby is the sun. So the idea was to see if we have a very faraway star, and the sun is in the middle, in between the star and us, then the sun should be deflecting the light that is coming from that star, and instead of seeing it in the actual position, we should be seeing the star at a slightly different position. So this is what astronomers wanted to see. The only problem is that if the sun is out, it's kind of hard to see the stars that are behind because the sun light is basically blocking everything. But then when an eclipse occurs, then this is possible because the eclipse, well, the moon is basically blocking the light coming from the sun, and then we can see everything that is happening near to the sun, and we can see the stars nearby. And then if we measure the position of these stars at this point, and then we compare the position the stars have when the sun is at a different position at a different epoch, we should be able to see that the light then of these stars was reflected during the eclipse. And this is what astronomers did in 1919, and they discovered that yes, indeed, Einstein's theory of relativity was correct. Now, we've talked here about eclipses in our solar system and how we use them and how they help science. But we also have other types of eclipses in the universe. And now I'm going to talk about it. So we already defined what the transit is, but I'm just going to repeat it. A transit then occurs when a planet passes between the star and the viewer. So we are the viewer, and if we are seeing a star very far away and a planet passes, that is a transit. So in the movie that I have here, and I'm not sure if it has started or not, let me try to put it again. There it is. So we're seeing that the brightness of the star is constant, right? But what happens if a planet passes in front of the star? And we measure this brightness as a function of time. We see that the moment the planet passes in front of the star, the brightness of the star decreases. It has some dip. So this can tell us that there is a planet there. And now, how can transits help us? Well, transits can help us determine many things. One of the things that this plot shows us is that there is a planet there. But from this, we can also infer other information about the planet. We can, for example, infer the site of the orbit of the planet. This is how far away from the star the planet is located. How do we do that? Okay, from measuring these changes in the brightness of the star, if we measure them for several times, we will see how long is the period of the planet as it orbits the star, right? And from that, we can infer what is the size, how far the planet is away from the star. Why do we care about this? Well, we care about this because habitability, that is a term that astronomers use to see if a planet could potentially host life. And how do we do that? Well, if the planet is at a certain location from its star where water could exist in its liquid form, and it has an okay temperature for life to develop as we know it. So if we know how far the planet is away from the star, then we can predict if it falls within the habitable zone and if life as we know it could exist there. But another thing that we can also learn from these transits is about the planet's atmosphere. So as the planet transits the star, some starlight will go through the planet's atmosphere. And that light can be analyzed to determine what kind of different atmospheric elements exist there. And, well, these elements can also tell us something about potential signs of life. So NASA has found thousands of exoplanets by observing these planetary transits. NASA had a Kepler mission. It was a Kepler satellite. It was out in space, but was specifically designed to explore the diversity and structure of exoplanetary systems. So with this mission that was in space, was active for over 9.5 years, NASA found over 2,000 planets, which is amazing. Right now, there are other missions looking for other exoplanets, but this is what I wanted to say here. Now, finding exoplanets, we can find exoplanets in different ways. Another way is by direct imaging. That is basically taking a picture of an exoplanet. But that is very difficult. Why? Because the light of the star is going to block us. It's not going to allow us to see the planets that are orbiting the star. It's as if we are trying to see a firefly next to a searchlight miles of distance away. So imagine that you're driving a car. When you're driving a car and the sun is in front of you, it's very hard to see the road, right? But if you put down your visor in the car, then you are able to see the road. So in a similar fashion, astronomers use a device that is called a coronagraph, that basically blocks the light of the star so that we're able to see the planets that are around the star. Now, these exoplanets are very dim, and we need a very good instruments in order to do this. The first coronagraph was invented a very long time ago, also by a French astronomer whose last name was Leo. And here I'm just going to show you a video that shows some planets, exoplanets orbiting a star. This system is called HR 8799. These are all gas planets. They are very giant planets. And this picture was taken from a telescope here on Earth. Now, this is very cool, but we are working towards paving the way to detect not only gaseous planets around the stars using coronagraphs, but also rocky planets like Earth, basically where habitability could be possible. So as you heard probably during the introduction, I specifically work with the Nancy Grace Roman Space Telescope mission that will be launched in 2026 at the latest 2027. And the coronagraph instrument, this telescope is going to have a coronagraph that is going to be the first of its type. This coronagraph is going to be a technological demonstration because it's going to be capable of seeing planets that are almost 1 billion times fainter than their star. And this will pave the way for us into studying the physical properties of exoplanets that are similar to Earth so that we can be a step closer to detecting more possibly habitable planets. Finally, I want to finish with this slide about eclipsing binaries. So most of the stars in our universe are not alone. Our sun is a very special case because it's a single star. But many of the stars in the universe are actually in pairs, and we call these systems binary stars. And so similar to transiting planets, eclipsing binaries basically cross in front of one another. So a binary star is a system in which the two stars orbit each other, and they orbit around a common center of mass. And if we plot the brightness, if we again look at the brightness of a star, probably with a telescope we won't be able to resolve both the stars. Probably this is going to be difficult. But if we look at how bright the star is, we might be able to infer more about this star and if it is a binary system. So in the plot that we have here, or this image, this video, let me see if I can play it. We have two stars that are orbiting each other, and what is happening? So the combined brightness of the two stars is constant. But as they move and one of them blocks the other, we see a dip in the brightness, right? So the biggest dip occurs when the brightest star is eclipsed by the companion star. And the shallow dip occurs when the less bright star is blocked. And so why do we care about these stars? Well, we care about binary stars because there are many stars in the universe. And if we understand how stars work, we can learn about many other objects. We can learn about if they have planets, we can predict how they will evolve and if they have conditions for habitability. But also, some quantities that we can infer from studying eclipsing binaries is that we can determine the period of the stars. We can also determine how luminous the stars are. Luminosity is basically what's the energy per time of these stars. And from that, we can also compute the temperature of the star and the radius of the star. And then if we know all these unknowns, we can also use Newton's gravity laws and Kepler's laws to derive the mass of the binaries. And why do we want to know the mass of the binaries? Well, because a star's life depends on the mass of the binaries. So the more massive a star is, the faster it finishes its fuel and the faster it dies compared to a star that is not as massive. Okay, with this, I'm going to finish the science part of this talk. I really appreciate your attention, and I'm just going to talk a little bit about myself. The reason why I'm invited here is because I am a role model for a NASA program, and in this role model program, I am expected to say a little bit about myself, and that's what I'm going to do next. So, as you can see, from my English probably, English is not my first language. I am originally from Mexico, and I'm going to tell you a little bit about my career path. So I did my bachelor in Mexico in physics, and bachelors in Mexico last usually 4.5 to 5 years. So I started studying there in 2007 when I was 17 years old, and I finished my bachelor's in 2012. At the moment, I did not know that I wanted to do astronomy. When I started studying physics, I wanted to do medical physics. But as I started going more into my final years of my bachelor, I started being more attracted to physics, and I had an opportunity to do a summer school in astrophysics in an observatory in the north of Mexico. And from there on, I decided that, okay, I wanted to do a master's in astrophysics. Before I started the master's, I was accepted at the program at the Space Telescope Science Institute. It was an internship, a summer internship in Baltimore, where I got the opportunity to work with data from the Hubble Space Telescope. So I was here in the US for a little while before I went to Europe, where I did my master's in astrophysics from 2012 to 2014. And you can see all these different flags from different countries, and that's because for my master's, I did this program in which I had the opportunity to take courses in 3 different universities in Europe. One of them was the University of Innsbruck in Austria. Another one was the University of Rome Tor Vergata in Italy. And I completed my dissertation, my master's dissertation in Germany at the University of Göttingen. The research that I did during this time, during my bachelor and during my master, was purely numerical. I was creating my own astronomical objects in the computer. For my bachelor, I was working on simulating neutron stars interacting with black holes. And for my master's, I did something super cool, which was simulating how to destroy exoplanets. That's basically how asteroids and something called planetesimals, which are the leftovers of when a solar system is created, can bombard planets within a habitable solar. In 2014, I also had the opportunity to visit Chile, where most of the observatories here on Earth are. And then in 2014, I started a PhD in astrophysics at Radboud University in the Netherlands and at Leiden Observatory. There, my research was also purely numerical. That means I was creating, again, my own objects, astronomical objects in the computer. I was coding a lot, and I was studying how stars like our sun, when they are old, interact with a companion star. And here you can see me, I was jumping at some party during my PhD. And then after I finished my PhD, I moved towards doing more public engagement and outreach. I moved to the UK, where I was taking some courses at the University of Cambridge about public engagement. And I also had the opportunity to work in a couple of projects. One of them was She Speaks Science, which is a project that aims to engage girls into science by means of storytelling. And I also worked for a little while as a science writer for a public relations company. At some point, I moved to Chile, where I got a huge grant from the government to bring astronomy into the classrooms in the country, but unfortunately, I could not continue with that project due to COVID. And I moved for a little while to work for industry. So I was working for Google, first as a technical writer and then as a project manager. Basically, all those annoying emails that you receive from Gmail sometimes, they were probably coming from me. We were creating emails just to let the public the customers know changes that were occurring within Google. And in 2022, I got a position at the Space Telescope Science Institute again. So you can see two pictures from 2012 and another one from 2022. Where now I work as an education and outreach scientist. Susan already explained all the projects in which I am involved. But I just want to say something else about myself. So not everything in life is work. I also do some other things. I put these emojis so you can figure out what my hobbies are. I like to read. I like to do photography. I love to bake cupcakes. As you can see, some of the cupcakes I baked last year. I also like to hike volcanoes with my partner. I like to run. I like to dance. And I love watching soccer, figure ice skating, and snooker. And one of my hobbies was basically doing public outreach. I had my own socials where I was creating infographics and videos, and now that hobby has become my job. And that's pretty much it. Thank you very much for your attention.
Thank you, Dr. Saladino. Did somebody have any questions for Dr. Saladino? She's willing to take a few questions if somebody wanted to ask her anything. Okay, we have one question over here.
Oh, okay. Hold on. Gotta take my. Here we go. Is this on? Yeah, it is. Here's a question.
Okay, thank you. You mentioned that most of the stars are binary stars, and that's the first I've heard that. I did not know that. What is the ratio? Do you have a kind of a ratio of how many are binary and how many are individual? I don't suppose there's any triple stars, are there? Are there? Oh.
Yes, there are triple stars. There are multiple stars. There are stars that are quadruples. That is correct. I don't have the ratio here right now, but for massive stars, it's a great majority.
Okay, thank you.
I'm curious how many women are in astrophysics, like at the master's or the PhD level. Are there very many women in the field?
Not that many as we would like to have, but there are. When I was doing my master's, the group was 13 people, and I think that 6 of us were women. So it was almost a 50%. And during my PhD, there were many women. I don't have the numbers exactly, but there were women in the program. Unfortunately, not many.
I'm going to jump in here just briefly. We have a program here that we do called Girl Power Science, and it's aimed at girls between 3rd and 8th grade. And it's an opportunity for them we're trying to promote more women in STEM. And so we always have a female subject matter expert talk about the work that she does. And a few years ago, with that Zoom call that she would present, and then our kids get to ask her questions. And so we actually had an astrophysicist out of Goddard Space Flight Center talking about the work that she does using satellites to look at carbon dioxide levels. And then during the question and answer period, one of our girls asked, "How did you get interested in astrophysics?" These are like 3rd to 8th graders. And she said, "Well, when I was in college, I was an English major, but my boyfriend was a physics major. We'd go from observatory to observatory. I eventually dumped the boyfriend, but I kept the astronomy." And now she has her PhD in astrophysics, and so score 1 for, and so we got a few more young women in here, so maybe we can plant some seeds here. All right.
Yes. So do we have any other questions? Yes, in the back.
So recently, some of our dwarf planets in our solar system have been discovered to have rings as they were occulting stars. And how can they tell it's a ring and not just a moon from that dwarf planet?
Like for dwarf planets, you mean? How can they know that it's rings and not the moon?
Right.
Honestly, I don't know. I don't want to give you a wrong answer. Planets are not really my expertise.
Thank you for the
All right.
honest answer.
All right, thanks. I guess we'll we have another question here.
Oh,
Hold on.
another question,
Sorry.
yeah.
Okay, so we get a total eclipse that comes real close to here on April 8th, I believe. It's a Monday for those of you that still have a day job. And we just got to drive about 150 miles west to get the full enchilada. Is that going to be a total eclipse or an annular eclipse?
In April 8th is going to be a total eclipse. It will be visible there's something called the path of totality. That's where if you are in that path of totality, in wherever you are in the world, you will be able to see the full total eclipse. I think that here in Baltimore, where I am based, we will be able to see up to 90% of the eclipse, so it's not going to be fully covered, like the sun is not going to be fully covered and you won't be able to only see the corona, but you will be able to, the moon is going to be able, you will be able to see that the moon is covering most of the sun disk.
Yeah, here at Kopernik, we'll be 97% covered. If you went to Syracuse, you'd be just into the path of totality. If you go to Rochester or Buffalo, Brockport, you'd be right down the center line. Olean. So.
Okay. All right.
Well, thank you again very much, Dr. Saladino, for your time and expertise. It was great, great information for us.
Thank you very much, Dr. Saladino.
Thanks for having me. And I hope you enjoy your night and tomorrow the eclipse, and in April the eclipse.
Thank you. Okay, you want to clear off the Zoom? Okay, and it's underneath the teacher resources. We have to go back to 2.0. Remember, it's in 2.0. Okay, and 2.0. Eclipses, October 13th. There it is. Enable content. Okay. Okay. All right. So welcome. I'm Dr. Susan Higley. I am a NASA Partner Eclipse Ambassador. So I'm going to talk a little bit about how that happened. I'm also the Director of Education at Kopernik Observatory and Science Center. So as a NASA Partner Eclipse Ambassador, we had a young lady who was an undergraduate student, Alexandra Zaleski, aka Sasha. She was interested in becoming an Eclipse Ambassador, and she's an undergraduate student. And she needed an amateur astronomer to partner with, so hence myself. And I am very amateur, so I'm not an expert. I was a math teacher, a principal, and a superintendent, so I don't have the science background, but I have the math background. So I did do a lot of science with the math, and I did a lot of work with NASA over the years when I taught down in Maryland, and I worked at Goddard Space Flight Center. So the Eclipse Ambassadors go through some training. So we attend live sessions, and it's put on by the Astronomical Society of the Pacific. And NASA supports that, and so NASA Heat will be mentioned throughout the presentation, as well as the NICENet network. And so if you know somebody that's interested in becoming a NASA Partner Eclipse Ambassador, they're still looking for them. So they try to pair up amateur astronomers with undergraduate college students to try to be advocates and educate and communicate about science, such as the eclipses. So these are two images from the March 2015 solar eclipse. So the left image shows a partial solar eclipse, and the right shows the total solar eclipse. So my question to you is, have you ever seen a solar eclipse? So who in the room has seen a partial solar eclipse? Okay, perfect. And who in the room has seen a total solar eclipse? So we have a couple. Okay, so if you travel just a little ways from here, you can see the totality in April, as you were asking your question about. I'm going to actually go up above Niagara Falls on the Canada side to see the totality. And we have about 3 minutes and 86 seconds of totality. So I'm going to kind of talk a little bit about the total eclipse as well as the annular eclipse tonight. So what's the difference between the solar eclipse and the lunar eclipse? So this is a simplified diagram to show the difference. So I'm going to need 3 young ladies to help be my volunteers. So I am going to ask if you would like to be part of this. Would you like to be part of this? Okay, come on up. I'm going to have you be my sun. Is the sun hot or cold? Hot. Hot. So you know what? You're going to have to put on these gloves, which are going to protect you from the sun. Okay, can you put these 2 gloves on? Perfect. Okay, you ready for the sun? Here comes the sun. Isn't he cute? Okay, you get to hold the sun. Okay, and I'm going to ask, would the young lady in the back like to participate? Come on up. How would you like to represent the Earth? Yeah, would that be okay? Okay, there you go. And then, would you like to be my moon? Sure. Okay, perfect. So they all have cute little faces. I couldn't resist, I had to have them. Okay, so if you'll be the moon. Okay, so right now we have our sun, we have our moon here, and we have our Earth. So notice that the moon is between the Earth and the sun. So according to our diagram, if the moon is between the Earth and the sun, which one do we have? We have a solar eclipse. Perfect. Now, if we take and reverse these 2, we now have the Earth blocking the moon some, so we have a lunar eclipse. Now, why don't we have these all the time? It stands to reason, you know, we have her going around the Earth. So just keep circling, keep circling. So she's circling around, okay? So meanwhile, the sun is also moving and spinning. You don't have to spin around, but you can turn him a little, okay? So he's very dynamic. It's always moving. And then we have the Earth doing its own little rotation on its axis, so you can spin right there too. Okay, just stand and spin. There you go. So all of this is happening. But why don't we see the eclipses all the time? Well, that's because this moon has a 5-degree tilt in an elliptical orbit. So there's only special times where we line up and get our eclipses. Okay, how about a nice round of applause for our young ladies here? Fantastic job. Thank you. Thank you. So we have the annular solar eclipse coming up here tomorrow. How exciting. We hope we get a break in the clouds. And then we have the total solar eclipse coming up in April. So just what exactly is an annular solar eclipse? That's okay. Okay, well, I'd first like to acknowledge NASA HEAT for all of the cool graphics you're going to be seeing throughout this. And this is the year, I'm going to talk a little bit more about the heliophysics and so the year of the sun coming up. So during this presentation, we're going to talk a little bit about the science and the safety behind viewing the annular eclipse as well as the total eclipse. We're going to talk about the NASA eclipse science, and we're also going to talk about how NASA is reaching out and trying to engage the public, hence why I'm here. So the annular solar eclipse. This is happening tomorrow on Saturday. 9 U.S. states will see this, as well as 48 contiguous states. So some will see the ring of fire, some will only see part of it. And we should see about 20% if we could see it from here. So science safety is very important, and that is NASA's #1 priority, safety for everybody. So we're going to talk a little bit about eclipse viewing safety. We're going to talk more about the annular eclipse, and we're going to talk about those key priorities. Now, at the end of each of these sections, there's going to be a short quiz. So you're going to have to participate. So you're going to want to pay attention because there's multiple choice and there's true and false. Okay? Okay. So eclipse viewing safety. So there's 3 things that are key with this. So is it ever safe to look at a solar eclipse? So that's one of the questions we're going to have to answer. How can you safely observe an annular solar eclipse? And what tools are available to make sure that we're safe? So you saw this graphic when Dr. Saladino presented it. So again, you have the sun, you have the moon between, and then you have the Earth. So when you talked about that path of totality, if this was going to be a total solar eclipse, this area here is called the umbra. And in this umbra, as this path rotates across, that's the totality, the range. The penumbra is this part here, and that's the area that will see a partial eclipse. So the moon's shadow has two parts, the umbra, the dark inner shadow, and then the penumbra, which is the faint outer shadow of the moon. Partial eclipses are seen within that. Now, in order to observe it, you're going to need to have these special glasses. These special glasses have a very special code. So when you look at the glasses, you want to make sure that you see that code right there. So on this particular pair of glasses, the code is written inside, and you can see it. So it's right here on the side. You want to make sure this is the glasses that are approved that will protect your eyes. And only certain reputable manufacturers have these particular glasses. So must have these. Are you going to wear sunglasses? No. Are you going to wear sunglasses? No. That will hurt your eyes and cause permanent retinal damage. So, one of the questions you're going to make sure you know. View the eclipse glasses with only special glasses, and regular sunglasses are not safe to view the eclipse with. So there is also indirect methods. So this one here is one indirect method. This is called a sun spotter. So this is a handmade sun spotter that Mr. Desker had here at Kopernik. So you can view it through an indirect method. There's other methods. You could make a pinhole projector at home. There is a paper out on the table. It looks like this. One side does talk about safety. The other side does talk about, again, are you going to wear sunglasses? No. You're going to wear the approved eye protection. And then also gives some directions and guidance to making a pinhole projector. There are also other pinhole projectors, such as this. This is by the Globe Observer, which is a mission, one of NASA's missions to study the Earth. And I'm going to talk more about it throughout the presentation. But there's what they call a pinhole in it. So there's a little hole. So you don't use this. You do not look directly at the sun like this. You will ruin your eyes. You use it to look down on the ground and have the sun go through and see the projection through the pinhole. So eclipse glasses, when you have the eclipse glasses on, it's safe to look at the sun. Now to put them on, you're going to make sure that you don't look at the sun as you're putting them on. You probably want to be looking down at the ground and then turn around at the sun and see what's going on. So just to be safe, to protect your eyes. Never look directly at an uneclipsed or partially eclipsed sun. So with the annular eclipse, you never want to take these off because the sun is never completely covered. It has that ring of fire when it's at maximum. So the people that see that ring of fire, the moon does not completely cover the sun. So you would hurt your eyes if you took these off. During the total eclipse, there are moments, depending on your location, of totality. During that time, when you actually hit totality, you can take them off for that amount of time to see it, and you'll see the corona. I had one of those activities where I had you making the corona. So this would be what you'd see in the total eclipse. But then you want to make sure you have them back on before totality ends. So never look directly at it. Don't use the eclipse glasses with binoculars. So Mr. Desker shared this one with me. This is what someone did with a pair of binoculars. Can you see the holes in it? So do not put these over your binoculars or over a camera. You can only use approved solar filters on telescopes and things. So you will burn your eyes yet if you do this. So don't put it over top of the binoculars. We do have, I had to come get it, a pinhole projector that Mr. Cardy 3D printed on our 3D printer here at Kopernik. So NASA put together some models that you could go online and get, and you could 3D print your own. So this was our first model. We're going to refine this. Mr. Cardy's going to have them probably available when we do the total eclipse in April. There are other methods as well. So this happened where somebody took and used a colander at home. So they put their colander out and they looked through the holes down to see the eclipse. So you could, as long as it has a circle and you could put it down and see through the holes of it and project it down on a sidewalk or something, you could use that. That's a pinhole projector. Make sure the sun's behind you when you do that. Okay, here's your knowledge check. Okay, so we're going to see how you do. So multiple choice. What we'll do is I will read the question, and then when I ask, so for instance, how can you safely view the annular solar eclipse? We're going to select all that apply. If it applies, I want you to clap. If it does not apply, do not clap. Okay? So how can you safely view the annular eclipse? Can you use A, eclipse glasses? Very good. All right. B, can we use sunglasses? No. Okay. C, can we use a pinhole projector? Perfect. D, can we use a solar filter? We're a little unsure of that one, I think. But yes, approved solar filters on telescopes and binoculars will be fine. So approved solar filters, yes. Okay. Which of the following are not considered a proper safety precaution to take while viewing an annular solar eclipse? A, viewing the solar eclipse with a pinhole projector. Oh, you guys got that one. Good job. Using a colander to project the eclipse on the sidewalk. Good job. C, wearing sunglasses or ski goggles to view the eclipse. Perfect. Do not do ski goggles. Don't use ski goggles. They will not protect your eyes. Perfect. True or false? So this one you're going to say true or false, whichever you think it is. True or false? You should keep your eclipse glasses on during all phases of the annular solar eclipse. Perfect. You guys are fantastic. So, just to check how you did, absolutely. Wear sunglasses or goggles to view the eclipse will never happen because you would ruin your eyes. So do not do that. Okay? And during the annular solar eclipse, the moon doesn't completely cover the sun. That's why we want to make sure we keep the glasses on the whole time. In 2017, people observed the eclipse path at totality were able to remove the glasses. That's the only time, and when it hits totality is the only time that you're allowed to remove them. And that will be in April, if you're in the path of totality, only. Okay. Some eclipse basics. What is an annular solar eclipse? So by the end of this section, we'll have to answer these questions and see how you do. So why does NASA study the sun? What's the relationship between the sun, the moon, and the Earth? What's heliophysics? And why do eclipses occur? So the sun's a star. It's a dynamic star. Dr. Saladino shared that with you, that it's very dynamic and there's a lot of things going on. NASA sent up NASA's Parker Solar Probe. That's going to be talked about a little bit later, and that's actually out there studying the sun. The sun goes through this cycle every 11 years. We are coming up on solar max. And so you're going to be seeing a lot and hearing a lot more about solar max because there will be aurora, a lot of aurora that might possibly be down here where we might be able to see it because of what's going on the sun. And it does go through an 11-year cycle when it hits the peak. So it kind of goes down like this and it just cycles. When it hits the peak, that's solar max. So we're coming up on solar maximum. The Sun-Earth relationship. So when I worked down at NASA Goddard at the on the Image Satellite Project, I had to learn about the space weather. And I did some education outreach activities working with Dr. Sten Odenwall and Dave Williams and Jay Friedlander. And I always thought, this is just me visually, I always thought this looked like Darth Vader laying on his side, but it's really the Earth's magnetosphere. But I always thought that's how I kind of kept it straight. That magnetosphere is what protects us from the solar wind and the radiation coming off the sun. And it comes down when the sun has one of those coronal mass ejections, which is a mass ejection of plasma from the sun. It comes to the Earth and it'll actually bend in this bow shock, which is the front part, and it'll come in and it'll funnel down the Earth's magnetic poles, and that's what causes the aurora. So when Dr. Saladino was talking about studying this stuff and how it impacts our communication, when there is a solar storm, it can impact us on Earth. In 1989, it knocked out the power in Quebec. So it can impact pipelines because the charged particles go down the pipeline. And so we really want to know about space weather, especially we're looking at sending astronauts back to the moon and back to Mars. So I'll cover them in a little bit later. So we want to protect them. So space weather is a hot topic down at Goddard. So what is the solar eclipse? The solar eclipse occurs, I'll see if I can get over there. There I go. When the moon moves between the sun and the earth.
A solar eclipse occurs when the moon moves between the earth and the sun, blocks the sun's light, and casts a shadow on the earth. When the moon completely covers the bright disk of the sun, that's a total solar eclipse, and it happens roughly every year and a half somewhere on Earth. A partial solar eclipse is more common, happening at least twice a year. A lunar eclipse, on the other hand, is where the moon moves behind the Earth, so it's now the Earth blocking the sun's light on the moon, creating a shadow on it with a red tint. The easy way to remember the difference is to remember what gets darker. With the solar eclipse, the sun gets darker, and during a lunar eclipse, the moon does. A solar eclipse is a rare event that not many get to see, because the moon's shadow is relatively small. This limits the locations on Earth that get to see it. You have to be on the sunny side of the planet, and you have to be in the path of the moon's shadow. So, if you find your area in the path of totality one year, you've hit the jackpot, because on average, that same spot on Earth will only get to see a solar eclipse every 375 years. During a solar eclipse, the moon casts a shadow with two parts, the umbra and penumbra. The moon's umbra is part of the moon's shadow where the entire sun is blocked by the moon. In space, it's a cone extending some 400,000 kilometers behind the moon. It's when the small end of this cone hits the Earth that we experience a total solar eclipse. Most eclipse maps depicting the path will show you a circle representing the shadow of the moon, but in actuality, the true shape of the umbra is more like an irregular polygon with slightly curved edges. This is because the moon isn't a perfect circle. It has mountains and valleys on its surface, which all affect the passing sunlight and subsequent shape of its shadow. And scientists now have a greater understanding of the shape of the moon's surface, thanks to NASA's Lunar Reconnaissance Orbiter. The unprecedented level of detail from the topographic maps, photos, and other datasets has allowed us to more precisely pinpoint the regions on Earth falling within the path of totality of a solar eclipse. So, if you get the chance to witness a solar eclipse, always remember that our little moon plays a role that's quite large.
So that's the total solar eclipse. And you mentioned that was 2017. You're absolutely correct. So we have over here the annular solar eclipse, a little map that looks kind of like this as well. And so on this, where the path of totality is, this will be for the total eclipse. So where the path of totality is, you can see those little ovals that they put that they just spoke about. That's, again, because of the shape of the moon and the craters that are there and stuff, that it distorts it. It's not a perfect circle. Now, each of these percentages are what the percent of the partial eclipse that they would see. So if you look at that one, it's the same as this, but I will leave this so you can look at it, so you can check it out, or we can pass it. It's okay to take a look at it and just see where you might want to, where the path is. So the annular eclipse, now what's the annular eclipse? That's different than the total eclipse because you have the ring of fire. It never totally
Roughly every year or two, somewhere in the world, the sun appears for a few moments as a ring of fire in the sky. This is called an annular solar eclipse. Annular comes from the Latin word annulus, which means ring. An annular solar eclipse occurs when a new moon passes directly in front of the sun but appears too small to cover it completely. But why is that? It's because the moon's orbit around Earth isn't a perfect circle, but rather an ellipse, or slightly oval-shaped. This causes the moon to move closer to us and then farther away during its month-long orbit. When the moon is at its closest point, called perigee, it appears slightly larger in our sky. When it's farthest from us, at apogee, it appears a little smaller. But we don't see an annular eclipse every month. That's because the moon's orbit is also slightly tilted in relation to Earth's orbit around the sun. This means during most months, the moon is either too high or too low to block the sun. So only when a new moon is at apogee and passes directly between Earth and the sun do spectators on Earth get the rare opportunity to see the ring of fire in the sky. Unlike a total solar eclipse, when the moon completely covers the sun, during an annular eclipse, the sun never fully disappears. So if you're lucky enough to be in the path of an annular solar eclipse, make sure to wear your solar eclipse glasses or use other safe solar filters to witness this spectacular ring of fire in the sky.
So during the annular solar eclipse, there's different phases. So the phases are according to how the moon is coming across the sun. So it starts off and you have a partial eclipse where it's totally coming across, starting to grow, get bigger, taking a bigger bite out of it, so to speak, as she said. And then you get the ring of fire. And then it decreases as it starts to move away again. So with your different phases. And again, the difference between the annular and the total eclipse is the annular, you get the ring of fire because the moon never completely covers the sun. And with the total eclipse, it covers the sun completely for a period of time. And then you do have the partial eclipse. So this is the path for the annular eclipse, which will happen tomorrow. And this is the path for the total eclipse, which will happen in April. The official NASA US map shows both overlapping, and that's what we're showing over here. So why we don't have an eclipse every month, I always called it, I think this is like Goldilocks. The story of Goldilocks. Just right. So that's why I related it to Goldilocks. 3 bears. So the moon's orbit is tilted at a 5-degree angle, which is why you don't see it all the time. The alignment has to be perfect. Okay, here we go. Okay, so you're going to, you can clap once. We'll save your hands because it might be a little bit of clapping here. So select all that apply. What 3 characteristics most accurately describe the sun? A, the sun is a star. Got it. B, the sun is a planet. Got it. C, the sun is responsible for almost all the heat on Earth. Perfect. D, the sun will likely be more active and dynamic this year than it was last year. You guys did fabulous on that. Perfect. Okay, 2, what's the study of heliophysics? We're going to select all that apply. So A, the study of the sun and how it changes. Good job. B, the study of the sun-Earth relationship. Nice job. C, the study of how the Earth's atmosphere is changed by the sun. Good job. And D, the study of how the sun affects the solar system. Fantastic. 3, why isn't there a solar eclipse every month? A, the moon's orbit is tilted. Good job. B, the moon is too far away. Perfect. C, the moon is too small. Perfect. 4, what needs to happen for an annular solar eclipse to occur? Select all that apply. A, the moon passes between the sun and the Earth. Good job. B, there needs to be a full moon. Nice job. D, the moon is at or near its farthest point from Earth. That one is a clap. Okay? So, great job on those. Nice work. NASA's key priorities and message for the 2023 eclipse. The number one thing, why does NASA observe solar eclipses? Dr. Saladino hit on that and talked a little bit about that in terms of exoplanets. What are NASA's priorities for the eclipse? They do have some priorities. And what are NASA's key messages about the eclipse? So NASA is going to be sending up balloons. They're going to send them up through the ionosphere, just like Dr. Saladino was talking, because they want to study what happens when it goes dark. So when the moon covers it and they have that dark time, what happens to the temperature? What happens in that area, in that region? So they're going to send some suborbital sounding rockets up there. Their number one priority is safety. Again, safety. Wear the appropriate glasses. Make sure that you have them on all the time during the annular eclipse. Total eclipse, you can take them off when it hits totality and get them back on before it moves off of totality. So make sure that you follow safety. That is their number one priority and number one message. They do want a broad participation. They're inviting all voices. So even if you can't see the eclipse, you can still participate. And I'm going to tell you some ways that you can do that. So I'm going to be having some links up here if you want to take a picture of the links, or there's some QR codes. If you want to hit those, you're welcome to do that with your camera and scan them, and it'll take you right to some websites too. So in terms of science, they have a number of missions in research and new discoveries that they're going to be asking for some participation in. Public engagement is a unique way to get involved. So go to where people are actually seeing it and experience that. In the science activation, they want learners to experience the science and do some stuff while they're experiencing the eclipse. Citizen science is gathering data for scientific analysis. So the key message is observe our star, observe the sun, and it can be safe and it can be inspirational. Experience the eclipse is one way that you can participate in a NASA science. And innovative NASA missions help us to study our star and the sun and how it interacts with the Earth. That sun-Earth connection is important. So by observing our sun, you need to be safe. Again, I can't say that enough, and got to repeat that. Make sure you use the eclipse glasses. Make sure you use a pinhole projector. Make sure you use a solar filter. And make sure that you're keeping your eyes safe. Experiencing eclipse is another way that you can do it. So there is a lot of unique opportunities to do that and some engaging activities. This picture is from 2017 when the sun was partially eclipsed. So there is missions out there that are asking for stuff, and there's missions out there that are studying. I did mention the Globe Observer earlier. I'm going to mention a few other things here. And those transits are important for finding exoplanets, the transits that Dr. Saladino talked about, and the eclipse knowledge that we've gleaned helped us find the element of helium as well. So there is a lot of science to eclipses. So, which of the following statements align with NASA's key message for the 2023 solar eclipse? We're going to clap once. A, NASA studying the eclipse to understand the Sun-Earth relationship. Perfect. B, safely viewing the eclipse is possible with proper equipment and or precautions. Perfect. The eclipse is a great opportunity for the public to engage in NASA science. Okay, D, all of above. Okay, now, we made a mistake because we're only supposed to select one. So it would really only be D. So, but that's okay. Okay, true or false? And when I get done reading it, you can shout out true or false. So true or false, the public can only engage in NASA eclipse activities if they're in the eclipse path. False. Perfect. True or false? By observing the eclipse on our own planet, NASA scientists can learn how to observe eclipses in other planets systems. True. Perfect. Okay. And now, believe it or not, there are partial eclipses on the red planet, and they're still possible. She did show some on Mars. She showed some on Jupiter. So Jupiter, Saturn, Uranus, and Neptune, they join Earth in being capable of having a solar eclipse and having total solar eclipses. They have moons that are large enough to do that. But unfortunately, we can't stand on their planet and see that. But transits aren't caused only by planets, exoplanets, asteroids, and moons. Kepler's mission was able to observe transits not only between planets and stars, but between stars and other stars. That was where she was talking about the binary stars as well. So eclipse science. So science that they do during eclipses is important, and the Sun-Earth-Moon relationship and the annular eclipse are important, and what do the NASA missions learn from these? So science done during eclipses, what we learn. So we can study our Earth's atmosphere. So I mentioned the ionosphere. It's not just the ionosphere that they're studying all the different layers of the Earth's atmosphere. Eclipses are a special kind of transit. So they use transits to test and find exoplanets and that it might be orbiting distant stars. And they do want to understand the ionosphere. And as she mentioned about the bounce is important for communication. And I'm going to have Mr. Desker talk about that in just a second. In terms of ham radio. So they find exoplanets by doing this, and you saw an example where she showed where the brightness gets dimmed, so the middle one does show that brightness and the dim in the middle there as well. And so they use this information that they glean to look for more exoplanets and to also better understand what's going on out in the solar system. So in addition to this, the Hubble Space Telescope spectral observations allowed scientists to detect sodium in the atmosphere of HD 209458, which was the first detection of a planetary atmosphere outside of our solar system. And this exoplanet is actually located 150 light years away from us in the constellation of Pegasus. So the Sun-Earth relationship, in terms of this, they're doing a lot of experiments. So in studying the ionosphere, the thermosphere, and the mesosphere as an eclipse passes over a certain location. So you saw this image that she shared, and so the ionosphere is that layer in the middle where the satellites are above it, and then you have a ground station as well, and so you can check the signals and look for irregularities that happen. And this is where Mr. Desker comes in to talk about how it relates to the ham radios.
Here we go. Have anybody still use an AM radio occasionally? All right. Have you ever noticed that at nighttime you can hear stations that are much, much farther away? And the reason that happens is because at nighttime the level of the ionosphere sort of changes, and the radio waves that are used for AM radio that bounce off the ionosphere tend to come down lower, and so they're able to ultimately you can hear that station further. So tomorrow there will be actually a ham radio group up here that will be contributing to citizen science, where we will actually be getting on the air on various frequencies prior to, during, and then after the eclipse itself goes on, trying to get a sense of how has the eclipse changed propagation throughout that evening, throughout that day. So you can actually see here, this is the eclipse that's going to happen tomorrow, the annular eclipse that's coming down through Texas, that we will in fact be, you'll see the shadow will come through here a little bit, and we will be affected. In April of next year, there'll be another eclipse, and we will be doing the same thing. We will have we'll be setting up equipment here again, and trying to get a sense of how propagation changes as throughout that time during the eclipse. So, if you are able to come up tomorrow, we'll have the ham radio stations, and you'll be able to sit in. And in fact, if you want, you probably even talk to a few people on ham radio if you'd like. So, all right.
Okay. Thank you. So extreme ultraviolet light from the sun is blocked during an eclipse. So when you're outside, you are getting exposed to ultraviolet radiation. That is one form of radiation that we have to be concerned about. So they're studying this because it would affect satellite drag. So when the solar storms happen that she mentioned, and she talked about that space weather, there can be radiation emitted from that. So we also are studying it because we want to make sure when we send our astronauts up that they're safe as well. So they study the moon to see what's going on, and so at any given time, location, a small valley, they want to look for the ring, the Bailey's beads. So they're studying for Bailey's beads to find the center of the solar eclipse. They use that to help them. And they use the moon's topography to determine that. What do NASA missions learn about the sun? The next slide, I showed it to somebody earlier, and he was amazed at how many satellites there are studying the sun. You ready for this? That's how many satellites are up there studying right now the Sun-Earth relationship. And if you scanned that QR code, it would take you to a website to show you some of those missions. Here's some missions that are set to be launched. So heliophysics, again, the study of the sun. Some of these missions are set to be launched. Again, they're clear out to 2025 and beyond. There's additional missions going out to study. Right now, the Parker probe launched in 2018, and to coincide with the heliophysics special year, when in 2024, they're going to have Parker probe is going to be closest to the sun, and they're going to finish off December of 2024 with the culmination of the Parker probe getting close to the sun. Solar Dynamics Observatory, it studies the sun. It does have a corona shield that she was talking about, a coronagraph on it. This Solar Dynamic Observatory, when I was working down at Goddard, I met a lot of the people working on it, and there's some dedicated individuals, and it's really cool some of the cutting edge science that they were learning at that time. So things are important in terms of the ionosphere and the planet and what how the sun affects us on Earth. Artemis. I don't know if you heard about the Artemis missions, but we're going back to the moon and then back on to Mars. And so the eclipses are important because they're studying as part of that the space weather, which we've mentioned multiple times here, because they want to make sure and protect our astronauts because the radiation in space from these space weather events can affect our astronauts. So that poses a risk to them during their journey to the moon and to Mars. So we want to make sure and try to do everything we can to protect them. Public engagement activities. So there is a number of initiatives and for you to get involved. So some of these initiatives are the NASA Science Activation. So NASA Heat is part of it. The Eclipse Ambassadors, which I am one of, the NASA Partner Eclipse Ambassadors. There's the Nationwide Eclipse Ballooning Project. There's the Earth to Sky Project. And then they have the Office of STEM Engagement, and that's where NASA Next Generation STEM comes in and NASA Connects. And the Office of Communications, the NASA Eclipse website, the NASA Heliophysics social media site, and then this big year, the Heliophysics big year coming up. So each month between now, October kicked off, and the theme of this month is the annular eclipse. You can probably guess in April of next year, the theme is the total eclipse. But there's a theme all the way through for every month, all the way through December of 2024. So NASA HEAT is located at Goddard Space Flight Center. It's the NASA Heliophysics Education Activation Team, and they want to help encourage STEM education and students to go into STEM careers. And we hope to inspire future scientists by that. And so to do that, things like that pinhole projector I showed you that they came up with, the 2 and 3D printed one. And there's going to be all kinds of lessons for all of this available for the public to share in. The Eclipse Ambassadors, again, I mentioned if you're interested in doing this and you're an amateur astronomer, pair up with an undergraduate student and apply to be able to do some outreach, and they provide some training for you. There's the NASA Eclipse website. There's a lot of information about this, this eclipse, as well as the one coming up in April, and they're constantly updating it with things and information. So there's a lot of activities on there to download that you could do at home with your kids, that you could do with your family. So take a look at that. NASA Heliophysics is pushing out stuff on social media. So they're on Twitter, they're on Facebook, and Instagram. Then you have NASA's Heliophysics Big Year, so they'll be pushing out something for each month that they're talking about and having contests and events throughout the year. You can get involved. So how can you get involved in these? Well, watch a live stream. We have a live stream tomorrow with Sasha, my partner, Alexandra Zaleski. So she's my undergraduate student partner. She's down in Texas, and she'll be live streaming from there, and we'll be sharing it through our YouTube channel. We'll also have it broadcasting out here in the lobby on our 2 TVs. So please come up and join us. The Exploratorium is producing 4 different live streams, and you can look at all those different live streams, whether you have an Apple or an Android. So there's the site for that as well. There's the pinhole projector, so you can take some of these activities and do them at home. And then it also has the pinhole projector box that you could make. What Citizen Science is doing, it's got the Globe Observer, it's got the Solar Jet Hunter, it's got the Planet Hunters transiting exoplanet survey satellite. And then you have the Eclipse Soundscapes. The Eclipse Soundscapes is very interesting because they want to have, they want your experience as a multi-sensory eclipse observer. So they want to know what happens when you go outside and the eclipse happens. So say it's the total eclipse. You go outside and you hit totality and it gets dark, or even almost dark. What happens? The birds think it's time to go to bed, so they stop and they go to bed. But what happens at night? Well, crickets start chirping. So they want to know, what do you see? What do you hear? What do you feel? Do you hear other people with you, like the oohs and the ahs? They want feedback on all of that, and they're trying to collect that data. Ham radio, as Mr. Desker talked about, they are looking at the ionosphere to see how it affects radio signals. Radio Jove is actually studying the sounds on the sun and Jupiter. And then there's the Stargazer project. The Globe Observer. You may have heard over the summer, there was multiple times I saw on the news where the Globe was asking for people to report what they heard, what they saw about mosquitoes and stuff. Well, the Globe is asking you to get involved, and they're asking you to participate. So I have here a number of Eclipse solar journals. So they make this accessible, and what they're asking you to do is record your data as you observe the eclipse and then report it to them. And then you're helping them with science. So these are available if you're interested in participating that way. Eclipse Soundscapes. Soundscapes project is looking for you to join. You can be an apprentice. You could go in there and you can learn about solar eclipses through a free online learning program and earn a certificate of completion. You could also be an observer. Observe these eclipses that are upcoming, the Annular tomorrow, and then the total eclipse April 8th of 2024. Go outside, observe with all your senses, and share them with the team. Collect data. Record that data and then share that data with the team. And help them analyze data. They would take participants to help analyze the data. There's the ham radio, and they're studying the ionospheric science. Whoops. And that's the Radio Jove, where we're listening for radio emissions, natural radio emissions from Jupiter, the sun, and our galaxy. There is additional resources. So there is a NASA Annular Eclipse website. I did print out that page that you see there on the side, so that was available for you to pick up if you wanted to. That also talks about safe viewing. Again, safety first. Make sure you wear your glasses. There's additional STEM resources here. So this is a really cool thing that NASA has come up with. See if I can get my mouse over here. There we go.
Braille is a 6-dot system that creates letters, numbers, any variation thereof. It's a language and it's all raised up so that it can be felt and so that you don't have to look at it, you can just feel it. So it's traditionally taught to people who are visually impaired or blind. And what it allows for is this ability to suddenly read and write. So what I have here is the tactile graphic book for getting a feel for solar eclipses. And I can actually feel the path of totality as it goes through each of the different states. It's really neat that they have outlined all of the state boundaries so I know just where I am on the map. But over here is actually how the solar eclipse happens. And this is a tactile version of just what's going to happen in the sky, because I can't see what's going to happen and a lot of people won't be able to either. So this allows me to feel how the moon and the sun are aligning and the earth, and I can really trace how one thing leads to another and leads to another.
And I have one of these laying out on the table, and we have another one, but that's a great way to be inclusive, and NASA's trying to be very inclusive. So by making accessible STEM resources, click back here, and then there is additional resources for the multilingual population. So they have the fact sheets in multiple different languages, they have glossaries in multiple different languages, and they also try to make the space place, NASA space place in different languages, and they're also trying to engage the indigenous population by including them as well. There is a NASA Eclipse newsletter. If you scan this QR code, you could sign up and receive the NASA Eclipse newsletter. And finally, I would like to thank all of these organizations because each of these had a part in this presentation tonight as well. So I thank them and I thank you for attending this event. Thank you. Thank you. That concludes our program for the evening. Thank you.